Shine a beam of light onto a clean metal surface inside a vacuum, and a strange physical reaction occurs. The metal instantly ejects electrons, sending tiny charged particles shooting off into the void. But here is the paradox. If you blast this metal with an incredibly bright, highly intense red light, absolutely no electrons are ejected. The metal remains completely inert. Yet if you swap that blinding red beam for a faint, dim blue light, electrons immediately shoot outward. This simple observation breaks the rules of classical physics. If light were just a continuous wave, a massive blast of intense red light should eventually build up enough energy to dislodge an electron, but it never does. This diagram maps the exact setup used to measure this anomaly. We have a sealed vacuum chamber containing a metal emitter plate on the right, which receives the incoming light, and a detector plate on the left to catch the freed electrons. Connect these two plates with a wire loop, and you create a closed circuit. That dial on the left is an ammeter, which allows us to measure the flow of those ejected electrons as a readable electric current. When scientists tracked this current, they observed zero time lag between the light striking the plate and the electrons ejecting. If light were a wave, a dim beam would just need time to build up enough cumulative energy to knock an electron loose. But because the metal doesn't wait for a buildup, the wave model fails. Scientists had to reconsider light as a barrage of individual bullets. This alternative model proposed that light is composed of individual, indivisible packets of energy. We call these packets photons. When a single photon collides with an electron, the transfer of energy is an instantaneous one-to-one event. But the metal emitter plate demands a specific minimum energy price, a toll known as the work function, before it allows an electron to break free. Lower frequency red photons simply do not carry enough individual energy to pay this toll. Because the energy cannot pool together, an entire flood of red light still fails to free a single electron. High-frequency light, like our blue beam, is different. A blue photon hits the metal, and its high frequency means it successfully pays the work function toll. Following the law of conservation of energy, any energy left over after that toll is paid transfers directly to the electron's physical speed. Looking at the formal equation here, the interaction acts as an exact accounting ledger. The photon's total incoming energy equals the metal's toll plus the resulting kinetic energy of the freed electron. This means an electron's kinetic energy is entirely dependent on the frequency of the incoming photon. The physical velocity of the particle is directly tied to the color of the light hitting it. To measure this speed, physicists use something called stopping voltage. This diagram illustrates the concept. By applying a negative electrical force to the detector plate, we actively repel the incoming electrons, trying to stop them from landing. As the kinetic energy of the electrons increases, a proportionally stronger negative stopping voltage is required to push them back and halt the current, as mapped on this lower graph. This chart plots the maximum kinetic energy against light frequency using real-world data for zinc. Right here on the x-axis, at the 10.4 mark, is the metal's exact threshold frequency, the precise toll where electron ejection begins. As the light frequency increases past that threshold into the ultraviolet spectrum, the required stopping voltage increases in a perfect, measurable diagonal line. This straight line confirms the transaction. As the frequency increases, the energy of the electron rises, in direct, predictable proportion to that frequency, exactly as the equation predicts. With the mechanics of frequency proven, we have to look at the final variable, the role of light intensity. Increasing brightness simply means firing more photons, not stronger ones. A brighter light ejects a higher volume of electrons, but the maximum kinetic energy, the speed, of those electrons remains exactly the same. Brightness dictates only the quantity of the energy transactions. The frequency of the light dictates the quality and power of each individual exchange. By treating light as discrete packets of currency, the photoelectric effect completely disproved the long-standing continuous wave theory. Recognizing this discrete energy transaction provided the framework for the development of quantum mechanics. The continuous macroscopic reality we experience is actually governed by strict microscopic ledgers of energy. The universe is dealt in fixed amounts, quantized at its core.